I'm starting. Now, as I said before, for the discrete time Fourier series, we have some finite number of Fourier series coefficients. If the period is capital N, then we have capital N distinct Fourier series coefficients. Normally, for the continuous time, we developed the forward formula, which is the representation of x in terms of the Fourier series coefficients and the harmonics. And we have also developed a methodology for determining the Fourier series coefficient ak from x, from the signal. It's a little bit more complicated than the previous case, but it's similar. Nevertheless, it's not our concern for the time being. For those who are curious about that, they may consult the book. I'll just write down the representation of the signal in terms of the Fourier series coefficients and the Fourier series coefficients in terms of the signal, the forward and the inverse transform. This is the representation of our discrete time signal. Remember that it's not x of t anymore. It's x square brackets n is equal to summation over k, and I'm not giving the upper and lower limits for the time being. I'll mention about that. The Fourier series coefficients times e to the j k omega 0 again times n, and this omega 0 is equal to 2 pi over capital N. All right? That is our representation. Now, in this representation, as I say, A0 is the same as AN, is the same as A2N, etc. And A1 is the same as AN plus 1. Or similarly, even is, in a more awkward manner, A minus 1 is equal to AN minus 1, is equal to A2N minus 1. Okay, so they are repeating itself with a period of n, capital N in other words. So this summation, inside this summation we should have only capital N distinct sums. And the methodology used in the book, or the form adopted by the book, is this. What is that? K in a duration of capital N. What could be possible summations? It could be from 0 to capital N minus 1. It could be from 1 to capital N. It could be from 2 to capital N plus 1. Things like that. Or it could be from minus something to N plus that minus something. For example, it could be K from let's assume n is equal to 10. So it could be, for example, from minus 4 to 5. Is that okay? How many items are there in this summation from minus 4 to 5? Minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. So there are a total of 10 items inside the summation. All of them are valid, and you may believe it or not, but of course you have to. They all give you the same formula for x of n. It doesn't matter where you start. All you have to do is you have to add n terms after that. Right? So this is the formula, or the representation of the signal in terms of the Fourier series coefficients and the corresponding harmonics. In order to develop a formula for ak in terms of xn, the methodology is similar to the thing that we did for continuous time. You multiply both sides with complex exponentials and you sum both sides of the equation, and then somehow you isolate an ak at the right hand side, and the formula for that ak will be that thing. And as a result, you should obtain this. And all you have to do is you have to remember this. So the inversion truly resembles the original formula. So this is the representation of xn, this is the representation for ak, and the summations are almost the same. This summation starting point doesn't matter anyway, similarly, but it must have a duration of capital N, and over here you have the periodic x of n, the period was capital N. This exponential expression has a negative exponent, whereas this one has a positive exponent. That's the only difference between the two, and there's also a scaling factor of 1 over n. So these two constitute the pair of discrete time Fourier series representation, which you have to remember in order to solve questions, as long as they are not very complicated, of course. But let's see our first example, which is the trivial example that doesn't require this formula, these two formulas. The representation here is, or the signal here is, x of n is equal to sine omega 0 n, and omega 0 is equal to 2 pi over capital N, with capital N is equal to I don't know, phi. So it's a pure sinusoid. If it's a pure sinusoid, what are the Fourier series coefficients is the question now. And the answer of that question will not require this formula, because as we know from continuous time theory, this sinusoid has two harmonics only. Right? The same thing that we will do. Let's write the same x of n using the Euler's expansion, 1 over 2j e to the j 2 pi over 5 n minus 1 over 2j e to the minus j 2 pi over 5 n. So this is the Euler's expansion, and it immediately gives you these two as the Fourier series coefficients, just like in the continuous case. This is a1, this is a minus 1, because here you have k is equal to 1, here you have k is equal to minus 1. But you have to be careful about what I have said before. It's just for the expression that you give as an answer to an exam question, for example. You really have to say it like this. It's not only a1 which is equal to 1 over 2j. It is a1 plus 5 times k, where k is any integer number, that is equal to 1 over 2j. Because a1 is equal to 1 over 2j, but a6 is also equal to 1 over 2j, or a11, a16, a21, they are all equal to 1 over 2j. And similarly, a minus 1 plus 5k is equal to minus 1 over 2j. So it's not only a minus 1, but a4 is equal to minus 1 over 2j, and a9 is equal to minus 1 over 2j, etc. It goes on like that. If you want to draw this thing, again, there's a problem about drawing imaginary numbers or putting values to imaginary numbers. Let's try to say it like this. Let's put 1 over 2j as a positive value, as if it's a positive, and then minus 1 over 2j will be the negative thing. So this is 1 over 2j at 1, and it's equal to minus 1 over 2j at minus 1. The original two harmonics. But we have other harmonics as well. This is 0, 1, 2, 3, 4, 5. Now this 5 point must be the same as this 0 point on the axis of k. And I'm drawing AKs over the axis of k. So this 5 will be the same as 0, which means at 6 you have this, and at 4 you have this. So these negative and positive things repeat themselves, negative and positive, and then around 10 they must repeat, around 15 they must repeat, etc. -1, -2, -3, -4, -5, that is similar to 0. At -4 you have this, and at -6 you have this. So this couple is repeating itself here, 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 etc. This is how you must express your result. So if you give me, again, the similar argument, if you say that by using the Euler's formula, this is A1 and this is A minus 1, if the question is like 10 points, then you will get 8 points if you give me this and this. Because it's not only A1 and A minus 1, but also all the other repetitions as well. You have to mention about those repetitions, and then you will get 10 points as the correct answer. If the question is more complicated, even if the question is more complicated, the strategy to answer the question will not be any different. For example, x of n is equal to 1 plus sine 2 pi over 5 n plus 3 cosine 2 pi over 5 n plus cosine 4 pi over 5 and plus pi over 2. Now as you see, it's a little bit more complicated than the previous one. The previous one was having only one sinusoid. In this question we have 3 sinusoids. Fortunately, these 2 sinusoids share the same period of 5. What is the period of this one? 2.5. Yeah, 2.5. 5 over 2, sort of. But that's not true, because 2.5 is not an integer number. A period must be an integer number. So it's not 2.5. Even this one has a period of 5, naturally. So the periods are common. I could make an indefinitely more difficult question from this one and ask it as a question in the second midterm by simply making this 6. Right? Because then the common period of all these things will be now 30, yeah. Very well. 30 will be the period, and 1 over 30 will correspond to the common frequency, omega 0. So be careful about that. Please try to answer the question, and you will see that it's difficult. It's not very easy. If this is 6, if I were a student, I wouldn't leave the classroom without solving the case if it is 6, because the teacher promised to ask it in the examination. Then why don't you just solve it and make sure that you will be able to solve it in the exam? You don't do that. That's a big surprise. So anyway, I'll continue with the easy case, which is 5, and I'll just try to represent this using the Euler's formula. This 3 with the same period will correspond to 3 over 2 and with a cosine, and this sign will make a 1 over 2j, which will share the same exponent term, e to the j 2 pi over 5 and plus, because these two are exactly the same sinusoids with the same frequency content, plus 3 over 2 coming from this cosine again, but from this sign it will be a minus 1 over 2j e to the j 2 pi over 5n. So how much have I considered yet? I have considered this dc plus these two coefficients. Now I have to consider this one as well. I didn't write that one yet. And I'll continue from here. Plus now this is the conjugate's positive term, positive angle term at the frequency of at the harmonic of e to the j times 2 times 2 pi over 5n plus 1 over 2 e to the minus j pi over 2. Now please take a look at these two coefficients. We'll try to explain it. E to the minus j 2 times 2 pi over 5 and normally without this e to the j pi over 2 and e to the minus j pi over 2, without these things, that would correspond to cosine 4 pi over 5n without this phase. With that phase, the angles convert to this. All you have to do is you have to say that 4 pi over 5n plus pi over 2 is equal to theta and expand cosine theta. And you will see that here it will be a positive e to the j theta or the angle phi, let's say e to the j phi, and here you will have an e to the minus j phi term. But these 4 terms in total describe everything. Why? Because this is A0, isn't it? Of course. What is this? It is A1. And it's a complex number, as you see, consisting of a real part and an imaginary part. This is what? A minus 1. Now how about this? Huh? It is A2. Because coincidentally, this is e to the j 2 times 2 pi over 5, which was 4 pi over 5. So this k here becomes 2. And automatically that corresponds to A2 here. And that is minus 2 here. So this is A minus 2. So we are almost finished. You will get 8 points by indicating these 5 Fourier series coefficients. These are the, however, 5 distinct Fourier series coefficients. And if things are a little bit more complicated like this, please do not waste any time and just say that AK is equal to AK plus 5 times an integer. Let's call it R. Just indicate it like this. Leave it like that. AK is equal to AK plus 5 times R for an integer R. Please don't forget to mention it. It means that it is periodically repeating with 5. There are 5 distinct things and they are repeating themselves. Are you already thinking of what would happen if this is 6? Now, I will show you only one example, but only one, from the discrete time Fourier series, which is this one. Because I'm not going to spend any time on the details of properties that can be used for the solution of questions in discrete time Fourier series. The properties are the same. Okay, we have listed how many properties? 8, 9 properties for the continuous time Fourier series. Similar properties will exist and they are given as a list of tables or tabulated as a list, let's say it. and they will be available to you in the examinations. You will, or I will, just copy them and give them to you in the exams. So you will have them. But of course, you should not depend or rely on the fact that they will be available to you. If you don't know how to use them, if you don't practice on how to use those properties, you will not be able to solve the questions because you will not understand which property to use. Okay? In order to do that, you have to exercise. Unfortunately, we're not going to do a lot of exercises here. We'll do only one. And one other remark. Since these are discrete time things, and usually the periods are some reasonable values like 5, 6, 8, 4, whatever. The formula that I have just erased from here consists of 4 elements, 5 elements, or 10 elements. Okay, it will be a summation, and that summation formula is always available to you, and that will be the correct answer. Of course, unless you can simplify that summation. There will be 5 terms of sinusoids. Can they combine to a smaller and more compact sinusoid, for example? But other than that, it's easy. It is not as difficult as the continuous time case, which requires integration. And from calculus, first year calculus, we all know that integrals are not easy to evaluate. But summations are easy. What is a plus b? It is equal to a plus b. You can leave it like that if you wish. But what is the integral of at from some limits, within this limit to that limit? You have to evaluate, you have to integrate, and that is difficult. That's why the properties are even more important in continuous time. In discrete time, you can just sum up everything and give the summation formula and say that this is the result. It may not be simplified. What will you get? You will get 9 points out of 10 because it's not simplified yet, but it will still be correct. However, in the continuous case, if you cannot integrate, if you cannot give me the formula for the integral, you will get, I don't know, 0 or 1. If the integral formulation is correct, you will get 1. Even if that's incorrect, you will get a 0, of course. But you have to integrate to get 9 or 10. So, what is this example that we will see now? The example is a rectangular pulse, and that is periodically extending. Where are they? That is from minus n1 to n1. So how many items of 1s are there inside this pulse? 2n1 plus 1. Because in the 0, that's also 1. So this is a pulse. And then it is repeating itself with a period of capital N. So the situation is something like this. Here you have a replica. Here is the original replica. And then it is repeating itself. So the period is equal to N. And the pulse width is equal to 2n1 plus 1. This is a discrete time periodic signal. You may find an analogy between this one and the continuous case of this. Right? This kind of a pulse shape we're looking for. So what are the Fourier series coefficients? Let's apply the summation formula. AK is equal to 1 over n summation k within a duration of n xk we are having a problem here. Let's write it n xn e to the minus jk omega 0. Now let's write omega 0 explicitly. What is that? It is 2 pi over capital N times N. So this summation is required for the determination of AKs. And how many distinct AKs are there? N, capital N. Now this summation limits of duration N. You must choose your best place. I guess starting from here and ending here, this is a suitable duration for the evaluation of the summation. What I mean is this. K from, it's not K, I'm sorry about that. N from here to here, one period. But we have xn. Now what are the values of xn around here? 0. What are the values of xn around here? All zeros. They are only non-zero from minus n1 to n1. So does it make sense if I write n from minus n1 to n1 only? Because in this duration, x of n is 1 times e to the jk 2 pi over n. So that's it. That is the formula. If n1 is given, for example, if n1 is 2, then it is from minus 2 to 2. Then you must sum these things for n is equal to minus 2, minus 1, 0, 1, and 2. 5 coefficients, for example. Suppose this capital N is equal to 10, I don't know. Then you have to just write down all the necessary terms one by one, and it will be a very long summation consisting of 10 items, 10 harmonics. Or 5 harmonics, in fact, from minus 2 to 2. But the general form for this one is also available, and all you need to do is you have to substitute the new expression or the new parameter of m equals n plus capital N. Capital N1, in fact. What I'm trying to do is I'm trying to make this summation to start from 0 and from 0 to 2n1. Why am I doing that? Because from 0 to something, exponential summation will give you a summation form that we know. Okay, that's what I'm looking for. That's why I'm trying to write this thing like that. But then the right hand side will be e to the I'm sorry, this must be minus e to the minus j k 2 pi over n m minus n1 naturally. And this term e to the minus jk minus n1 will be a constant term and can be taken out of the summation. So let's do that. 1 over n e to the jk 2 pi over n times n1. Then we have a summation m from 0 to 2n1 e to the minus jk 2 pi over n m. Now as you see, even this is one of the simplest Fourier series coefficient things, but even for them the generic expression is taking some time, as you see. But let's go on. Do you remember the finite summation formula for exponentials? Or the power terms? Summation k from 0 to n a to the k. Do you remember this? If k is from 0 to infinity, do you remember it? Yeah, what is that? It was 1 over 1 minus a. Let me tell you. This one is not 1 over 1 minus a. It is 1 minus a to the n plus 1. 1 minus a, or something like that, right? And in this formalism, that's what we are going to use. This is not a to the, but it is e to the, and the power term is n. So e to the k 2 pi over n. Take this and call it a. Then it will be a to the power n. Summation from 0 to 2n plus 2n1. So that summation will be this. First, let me write the left-hand side constant coefficient, which is 1 over n e to the j k 2 pi over capital N n1 times, let me open a big curly parentheses here, 1 minus e to the minus j k 2 pi over n times 2n1 plus 1 divided by 1 minus e to the minus jk 2 pi over n. Alright, and that's it. But this is valid, unfortunately, for k different than 0, because at k is equal to 0, there is a 0 over 0 ambiguity. The numerator will be e to the 0, so this will be 1 minus 1. And the denominator will also be 1 minus 1. So 0 over 0 will occur. So let's say that this is for k different than 0. For k is equal to 0, you have to separately evaluate. Or if you wish, you can apply the Hospital's rule. So this is the answer that you can give, and you can get full credits, 10 points. However, if you could further simplify it, I can't do that, by the way, to this, then you will get an extra 10 points, which is all bonus. But since it's written in the book, I can do it now. And I'm telling you that this thing corresponds to a sine something over sine something else. And again, as you see, a sine of 0 comes if k is equal to 0. Sine of 0 is also 0. And in the denominator, it's another sine of 0, which is again 0. 0 over 0 appears if k is equal to 0. So you shouldn't evaluate it at k is equal to 0. The idea to simplify the top figure from here to here is as follows. You are trying to make a balanced plus and minus e to the j theta and e to the minus j theta terms by multiplying with this one, here and here. So those balanced e to the j theta and e to the minus j theta terms will simplify to a sine. And similarly, it will also simplify to a sine in the denominator. Of course, I wouldn't request you to do that. However, in the tables, the Fourier series representation of that question in the very beginning is already given like this. So what can you do? You can use this to find the Fourier series coefficients of some other periodic signals, which are like not derivatives but differences, linear superpositions, etc., combinations of that signal with another signal. Now, all I will assume is that it is given in the tables and you can use it. Or the question can even be something like this. What is the Fourier series coefficient of that signal for n1 is equal to 2 and capital N is equal to 10? all you have to do is you have to substitute n1 is equal to 2, n is equal to 10, and write it down like this. That will be your answer. So I don't expect you to derive it, but I expect you to use it, okay, for this typical signal. All right. Now, as I said, the properties are the same for discrete time and continuous time. By the way, we haven't developed A0 because this is for k different than 0. However, A0, now this one, I want you to tell me without doing any calculations. Not from here, not from anywhere. Just look at the question and tell me the DC. No, of course not. It is all positive, so there is an overall positive offset. It's not positives and negatives cancelling each other. It's positives and zeros, and positives and zero. There is a DC. 2. Yeah, 2 and 1 plus 1 over n. Thanks. That is the DC coefficient. It's just the average value within a period. Okay? So there's nothing fancy about it. Normally that's always the case. You find the DC quite simply by looking at the shape and finding the area. And normalize the area with the period. That's it. The properties, let me give you at least a list, or give me the pointer to the list, is given at page 221 in Oppenheim's book. Please do refer to that. I'm not going to repeat them, and I'm not going to use them in any of the questions except for filtering, which we will continue tomorrow. There was a question, yeah. Yeah. M is equal to n plus n1. And so m is, if n is from minus n1, plus n1 will start from 0. M will start from n 0, and it will go to n1 plus n1. Yeah, this is the substitution that you make. And how many summation terms are there from 0 to 2n1? 2n1 plus 1. So the number of summation terms is the same here. Okay? We'll continue tomorrow.